Hello children, how are you all? Hope you all are doing well. This is VKM. Welcome to Electron Chemistry Center. In this video lecture, we are going to talk about continuation of previous topic that is states of matter. Again, we are discussing states of matter. As you know, in previous class, we are done with the Dalton's law of partial pressure. In this class, we are going to talk about Graham's law of diffusion. Graham's law of diffusion. Graham's law of diffusion. Before going to Graham's law, let us talk about a few terms. One is called diffusion. What is meant by diffusion? If you just place an incense stick in corner of a room, though if you lighten that incense stick, of course, right? If you just simply keep it, you won't smell it, right? You must lighten the incense stick. If you lighten the incense stick and keep it in a room, though you are in the other room also, but you can sense the smell because of the gas which is releasing from lightening of incense stick gives the gas, and that gas spontaneously mixing with the other gases which are present in the atmosphere. That means gas is actually diffusing. Gas is actually diffusing. It indicates a spontaneous intermixing of the two gases. Spontaneous intermixing of gases can be called as a diffusion. That is, a definition can be given for diffusion. So it is spontaneous because it occurs on its own. That's why it is spontaneous. Let me write it as it is spontaneous intermixing. It is spontaneous intermixing of two gases is known as diffusion. Nothing but gases are traveling from one pressure region to another pressure region. So from high pressure to low pressure, those are traveling. In another way also you can say that is traveling or spontaneous movement of the gases from high pressure region to low pressure region is also called as a diffusion. That is also another definition can be given. There is one more term, children, that is effusion. Effusion is nothing but escaping of gas molecule, escaping of a gas. Effusion is nothing but escaping of a gas from a container into which it is placed. Actually, wherever you have placed it, escaping of a gas from a container through a small hole, or else we can say orifice. Orifice is also called as hole. If you take a gas in a container, if you make a small hole or orifice into that container, gas starts to escape from the container through that small hole. That phenomenon is called as effusion. Both of these terms actually can be explained by the help of Graham's law. According to Graham's law, what is the statement can be given? Statement of Graham's law, if you observe it. What is the statement? Rate of diffusion is inversely proportional to its molecular weight. That means, okay, rate of diffusion of a gas, better. Rate of diffusion of a gas is directly proportional to its molecular weight, inversely proportional to molecular weight or molar mass or density. That means inversely proportional to square root of its molecular weight or molar mass or density can be taken. Rate of diffusion of a gas is inversely proportional to square root of its molecular weight or molar mass or density is taken as statement for the Graham's law. What does it mean? Rate of diffusion, that is R, is inversely proportional to square root of the molar mass, or I can take it as R is inversely proportional to square root of density, because you are aware of it. Pm is equal to, that is okay, we have PV is equal to nRT, right? So that is D is equal to D is equal to Pm by RT, that is nothing but Pm is equal to dRT, that is density is directly proportional to molar mass, right? That's why we can take either molar mass or you can take density, because density is directly proportional to the molar mass. Here R stands for what? R can be taken as rate of diffusion or rate of effusion. Anything can be taken. Rate of diffusion or effusion can be taken. R is inversely proportional to square root of the m, and R is inversely proportional to the square root of the density. And this rate of diffusion can be given it as volume of the gas traveled per unit time taken for the travel, actually. Okay, volume of the gas traveled upon time taken can be taken it as rate of diffusion. This I can simply give it as R is equal to V by T, right? Or else I can give it as rate of diffusion or effusion, of course. Rate of effusion, which is again R, which is in turn equal to number of the moles of gas, number of moles of gas effused, number of moles of gas effused per unit time. Per unit time, how many moles of the gas is effused, that is also can be taken. So I can write it as R is equal to N by T. That is also fine. Either you can take how much distance a gas is traveling per unit time can be taken it as rate of diffusion, or else how many moles of the gas is actually effusing, that is also can be taken. R is equal to N by T. And I can write it as whenever a gas is effusing or diffusing, there you can see the pressure drop. That pressure drop per unit time, you can see the pressure drop. So there is a decrease in the pressure, of course. Pressure drop per unit time can be taken it as minus dP by dt, or else I can take it as minus delta P by delta T. Here minus indicates that there is a decrease in pressure. That's why I've taken minus dP by dt or delta P by delta T. But minus dP upon dt is nothing but instantaneous rate of effusion. If it is instantaneous rate of effusion, then you can use dP by dt. Delta P upon delta T, in the sense it is average rate. Whenever if rate of effusion is average, then in that case I can use minus delta P upon delta T. It is instantaneous rate of effusion means dP upon dt. So if it is two gases, let us say if two gases are there, then R1 by R2 is equal to square root of M2 upon M1. But you are aware of it, R is equal to V by T. In that case, I can write it as, instead of R1, I can write it as V1 upon T1. It is V2 upon T2. That you can write it as V2 upon T2, which is in turn equal to square root of M2 upon M1. So I can write this as V1 upon T1 into T2 upon V2 is equal to square root of M2 upon M1. For suppose if both gases are traveling in same time, that is if T1 is equal to T2, I can write it as V1 upon V2 is equal to square root of M2 upon M1. Now if they are traveling for same distance, like same volume they have traveled, both the gases. If V1 is equal to V2, then in that case I can write it as T2 upon T1 is in turn equal to square root of M2 upon M1. It all depends on the question, whatever it is going to give it in the theory or in the numerical. Okay, and or else I can write it as this R1 upon R2, which is also can be written as D2 upon D1, because it is directly proportional to density also, and so it is inversely proportional to density also, and moreover it is inversely proportional to molar mass. But you are aware of it, M2 upon M1. Molecular mass is nothing but 2 into vapor density, that is VD2, of course. Yeah, this one is going to be VD2. 2 into VD2 upon 2 into VD1, vapor density. So this I can write it as 2 gets cancelled, vapor density 2 upon vapor density 1. R1 upon R2 is equal to square root of vapor density VD2 upon VD1 can be taken, isn't it? So this is also another formula can be taken. It all depends on the question. But generally, if you notice it, if you observe it, in general, this rate of effusion, if you notice it, R is proportional to P into A naught upon square root of M into T. You can take A also, that is also not an issue, rather than taking it as A naught. So here P is nothing but pressure, partial pressure or pressure difference of a gas, I can say. A is nothing but area of cross section, of a hole or orifice, because effusion concept is applicable whenever if you make a hole in a container, right? So Pa upon root over m into T, where T stands for temperature in Kelvin. T stands for temperature in Kelvin. It is the general formula. Can be given. R is proportional to P into A upon square root of M into T can be taken. Now, in a similar way, for suppose as you know that for a given volume of vessel, that means volume is going to be the constant, volume of the container is V, that is going to be constant for a given volume of vessel, that P is directly proportional to temperature. That indicates temperature increases, pressure also increases, then rate of effusion also increases. As temperature increases, pressure also increases. By that, you are applying more and more pressure. If you apply the more pressure, rate of effusion is also, that means more and more amount of the gas is trying to escape as pressure increases, isn't it? In that case, so that is R is directly proportional to the P here itself. R is directly proportional to P in the sense, I can write that R1 by R2, isn't it? That is P1 upon P2. Anyway, we have M2 upon M1. It can be taken it as like this also, because R is proportional to P, inversely proportional to M. If both are actually, both the gases, if I take two different gases, both the gases are escaping through the same orifice. Let us say if two gases are escaping, if two gases are escaping through same hole, that means area of cross section is same and temperature also same, then in that case the relation can be given as R1 upon R2 is equal to P1 upon P2 into root over M2 upon M1. It's very important formula, and as well as you are aware of it, in previous session we had discussed about Dalton's law. According to Dalton's law, partial pressure of a gas A can be given it as total pressure into mole fraction of A. Partial pressure of B is equal to total pressure into mole fraction of B. For suppose if I take PA upon PB, P total gets cancelled, chi A upon chi B, that is mole fraction of A upon AB. Mole fraction of A upon AB, that is Na upon Na plus Nb, and it is Na plus Nb upon Nb. Both gets cancelled, right? So what we are going to get it? Na upon Nb. In another way, I can write it as P1 upon P2, which is equal to N1 upon N2. Can I? Isn't it? So you can substitute in this formula. R1 by R2, which is in turn equal to N1 upon N2 into M2 root over M2 upon M1. It is also another formula can be given, right? So such a way, all of these formulae, you have to remember it carefully to solve the numericals based on Graham's law of diffusion. So all the gas laws are completed, like Boyle's law, Charles' law, Avogadro's law, Gay-Lussac's law, Dalton's law, and in this session, Graham's law also is completed. In the next session, we will be solving some numerical questions based on this. Hope you like the video. If you like it, please click on the like button, and we will catch up in next video. Please subscribe to Electron Chemistry Center channel. Thank you. Signing off.